Got another crazy idea today. We're talking about brain waves and essentially the formation of our brain structure around the complex volume or the Calabi-Yau manifold. So this is essentially a little representation of the neural network in our brain. And one thing to keep in mind is that if we're in three dimensions, we actually don't see 3D. We can't see all three sides at the same time. We really only see two sides. You take any object and you try to look at it, and you can't see the back and the front. There's always going to be a side that you just can't see. And so we technically always have two-dimensional projections of 3D objects. So this 2D, 3D switch back and forth is the conversion is kind of really fundamental to this because we have this complex volume, which is 3D. It's a complex volume that's 3D because uh, we have these points, say, give it a position x, just in one direction here, x and x in two dimensions, in 2 points here. You could draw a line between them, right? Um, of course, you could have an x, you could have a y, and a z, so you could have three different lines pointing around. But each one of those points is going to be connected to a wave function. So we put an amplitude at that point x, and another amplitude b at point x, at some other point. So we have two different points, and they both have sort of amplitudes. And the amplitudes is about this wave function here. And this wave function is a function of frequency and phase. Frequency and phase. And frequency is essentially frequency times time, and the phase is also going to be uh, another type of frequency times time, but they're different frequencies. Okay, so this phase angle has sort of a different type of frequency. I'm going to consider it the orbital frequency, versus this here is the oscillation frequency. Orbital versus oscillation. All right, and I'll actually put that right here. So we have the orbit, orbital phase. This is really because of the phase. This is the orbital phase, and this is an oscillation frequency. Okay, um, oscillation, whatever. Okay, and this is the orbital. Let me put the word frequency here. Okay, so frequency and phase. Now, now if we take a look at two different points on our brain, right, they're going to have maybe two different frequencies, right? Frequency one, frequency two, one and two, right? And of course, if you take any kind of frequency difference, you're going to get some sort of hertz. You get a beat. So you actually get a beat when you have frequency differences. And so now we actually have brainwaves. So we can take any 2 points along in our brain, and we can essentially assign frequency values to them. And so according to the quantum states, the evolution of the quantum state itself, usually this is like a loop, and you're looping around, e to the I. This here is like how many different ways you can make this equal to one, right? So there's an infinite different ways that you could do this, but that's just an oscillation frequency, and there's two different ones. And yeah, so you get the beat, so you get the brainwave, alpha, beta, gamma, delta, all that good stuff, from frequency differences between the quantum states in our brain. Now, what's interesting though is the second part, because the first part's pretty normal. Like we know about frequency differences, we know about brainwaves. It just gives us that. That's pretty standard stuff. But the second part's really were more important because in the second part we get this orbital frequency, or we get this phase difference. And I was thinking about it kind of like it's the spatial lag. So you can see where you have sort of this, if they were both going at this proper time speed in this direction or so, they would both be moving at the exact same uh, phase. So they'd be moving at the speed of light, proper time. But if one of them had some sort of a phase difference, then it wouldn't be going at the exact same like velocity and time as the other one. So you'd have this rotational sort of degree here, and you'd see that, uh, well, you could sweep out a little a little circumference here. Okay, so we have this sort of a distance that you can get from taking the angle difference, the phase difference divided by the wave number. Well, there's other ways that we can get area here. What I'm essentially trying to do is derive geometry from a phase angle. You know, we can get curvature from a phase angle. As you can see, there's a little curvature from our phase angle. Okay, and there's a lot of different ways we can calculate this area value. So you could take the Laplacian, integrate that over area. You could take the just a regular old gradient, um, and integrate that over area. We're doing it in this way. Let's consider a phase field. We're all over the place. There's always going to be just the same phase difference, which is essentially going to be kx squared. We'll set k equal to 1 just to make it easy. And then we could say, okay, let's take the Laplacian of this. Would be the second derivative in terms of spatial coordinates here. And you can get 2k out of that thing. We don't have y, we don't have z, so we're just going to get the derivative would be 2kx, and the second derivative would be 2k. So then we just put 1 for that, and we get a curvature of 2. Well, we get a Laplacian of 2. And then from here, you can sort of plug that into your curvature equation, and you can get a curvature. Another way is to think about it this way. You could say, oh, let's take the metric tensor. We'll take Minkowski flat tensor, and then we're going to come up with some sort of a tensor that's a function of the phase angle difference in terms of the position. So there's a lot of different ways that we can sort of derive curvature from this phase angle, and let's consider r being the distance between two nodes, and the phase angle between those two is going to give us the geometry or the curvature, right? And so we have this we get this 2D area really. So we're seeing we can get an area uh, from 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 uh, from this curvature because you have a distance, you have an angle, integrate that, you get an area. All right, so how does um how does this area work? Because we have this brain, we have a 3D brain, right? Well, not really. Actually, the 3D is more like a 2D surface, but it's like curved and twisted and stuff, so it looks like it's 3D. It gives you this illusion that it's 3D. But really, it's called tubular ventricles, right? And there's these little gyri in the Solchi that are kind of just like folding things up and curving around, just kind of building this thing. So it's really the surface area that's curved, and it looks like a 3D volume. Um, and that's kind of the nerve impulses can sort of flow between those uh, tubes. So that's why we have surface areas in our brain. And so this is essentially a representation of the anti-de Sitter conformal field theory um, idea. And here's how we can derive neural potential fields. Is we're going to get sort of this kernel, which is the interaction string. And we can take the voltage, we're going to integrate that over the, it's kind of like how we're doing an integral over the Brillouin zone for, or condensed matter. But in this case, we're taking the integral over the bulk uh, geometry, integral over the bulk space. And so we have this interaction string, which comes from, say, those two positions, and then to some power. Okay, so that just kind of tells you the strength of interaction between two distances. And you can get the curvature from the phase angle, and integrate that over a volume, and now all of a sudden you get this voltage potential. Uh, so, so this is how we can get sort of brain neural dynamics from a couple of different wave functions in two different quantum states. We can actually derive a volume, a geometric volume, geometric properties from this phase angle, which forms curvature, which is kind of like leading us to this uh, gravity, right? Quantum gravity. And then we have the frequencies over here, which is going to give us the brain wave oscillations. So that's pretty cool. Um, and this cavity yaw manifold is really interesting. You can see how this forms fractals. Everything from a coral to like walnut shells, to actual like seashells, curving around and stuff. The reason that we have these things forming is because this is essentially the lowest energy. So energy goes down when we go to sleep. We're trying to get to sort of a lower energy state, higher entropy state. Let's consider this first, though. If we have new thoughts, what we might be doing is quantum tunneling into new configurations, new things that we haven't been to before, because these things would all be new numbers, right? We'd have to quantum tunnel into those new configurations, and new thoughts just appear out of nowhere, right? This is essentially a deformation of the curvature of the manifold. So you're going to get like a warped side to it because all of a sudden you popped into some new position, right? But then the reformation of this curvature is essentially what happens when we sleep. So again, the energy is going down, the entropy starts to go up, entanglement starts to go up, meaning your thoughts become more connected to each other, so more easily accessible at future times. And the curvature is going to increase because things are getting closer together, essentially. When things get closer together, the curvature starts to increase. As you can see, kind of what would happen here, if these two things become really small, then this kernel becomes really large, and so the voltage becomes large. So this is kind of very interesting stuff, and this all has to fit very quite perfectly into this little idea that we have holomorphic, complex manifolds mapping to our brain neural network. It's a little bit crazy, but I think it's quite interesting and fun, and because this is essentially quantum gravity representation in our brain. It's so cool. So, anyway, thanks for watching. If you want to get one of these cheat sheets downloaded, have one for free at freephysicsmap.com. That's only for regular mechanics, regular physics. This is more like brainwave mechanics. But if you want to get one of those free cheat sheets, it's at freephysicsmap.com. I'll have that in the description. Thank you all for watching, and you'll have an awesome day.